This is the area which we call the OChem zone. The year is 2017. The setting, the University of Oklahoma. We come across 3 OU undergraduate students, 2 high-achieving students in organic chemistry, and 1 not so much.
This final's gonna be rougher than a bareback bronco riding angrily in a rose garden. These nerds know their stuff. I'll pick their brains.
Why are we here?
I keep seeing something, and I reckon you know your way around this OChem business.
What do you mean?
Y'all are liking to ace the next test, I figured. I seen it. I'm tired of failing these tests.
Okay, we'll help you.
How do you remember these darn tootin' pKa values and keep them in line? Dr. Science is crazier than a road lizard on a hot summer's day if he thinks that we can remember all this.
Yeah, like areosterics and counterions. You don't normally see simple carboxylics on his tests, so it's important to understand why as opposed to what.
So what makes a molecule more acidic than the other?
pKa number's lower.
Right, but that's only quantitative. What if we want to compare 2 molecules that don't have tabulated pKa's, or if they have multiple functional groups? We use areo.
What's areo?
Areo stands for atom, resonance, induction, and orbitals. Essentially, when acids are deprotonated, they leave behind a negative charge on a molecule. How stable this conjugate base is compared to the acid determines which one is favored in equilibrium.
A stands for atom. Remember that electronegativity is how well an atom holds onto an electron, and oxygen holds onto a negative charge way better than carbon. The greater the electronegativity, the better an acid it is.
R stands for resonance. Double bonds are the key here. A molecule that has to stabilize a negative charge next to a double bond can resonate, or vibrate, and spread that charge out from 1 atom to 3. That double bond essentially becomes a 1.5 bond.
I stands for induction. This is when negative charges have a lot of other atoms around them. Take this molecule, for example. These chlorines are all very electronegative, so if you remove this proton, they'll stabilize and pull off this extra electron, making the overall molecule more stable. Basically, the more electronegative groups around this leaving proton, the more stable the conjugate base is.
O stands for orbitals. Negative electrons held closer to a positive nucleus are more stable, and thus, the smaller the orbital, the more stable the atom is.
Okay, and what exactly are these sterics and counterions?
Sterics basically apply to bulkier acids and bases. When you have so many different functional groups and such a long carbon chain, you get some overlap. And these groups don't want to be next to each other. So a molecule will twist itself into a low energy form that keeps all its groups away from each other. This builds a kind of cloud around the negative charge and it makes it less negative from the outside. Counterions will help with that shielding.
Okay, this is starting to make sense. This acid-base business is clearing up a bit. And that's all there is to it.
Well, actually, recognizing the conjugate of an acid helps you identify nucleophiles, and recognizing a strong base helps you see E1 versus E2. We won't dive into the nitty-gritty, but basically, the conjugate base of a strong acid, such as the iodine ion or the bromine ion, is a great nucleophile because of how electron-rich it is, and how stable it can hold a negative charge. They also make great leading groups because of how stable they are on their own. For elimination reactions, it is important to recognize a strong base and notice how it will tend to go to E2.
But remember, this all has to do with stability.